Okay, I'm going to start a little bit here early because I got a meeting, and so I'm going to do something slightly different that's going to propel us forward based upon what we had before. And this is a problem that came out of that section. Let me quickly do though. Okay. I'm going to do this and then drop out of the. Hang on. Oh, I hope I don't have to do that. All right. Oh, while I'm doing this, let me make sure that I'm actually being streamed. Because sometimes I think something's happening and it's not. Oh, while I'm doing this, let me make sure. Oh, looks like I am. Okay. This is spring. This is statics. And I don't know why it didn't go to the content. I directed it to do that earlier this semester. Don't know why. Being from Louisiana, we make up our own words. How about that? I don't know what that word means, but there, if you want to know how to spell it, there it is. Let's just make up a word. Then, let's get back to work. Okay. Got a weird situation here. Okay, so let's read what he wants us to do. And then we're going to look in here what we want to do as an engineer. So the first thing he says is to replace the load on the frame by a single resultant force. Specify where its line of action intersects a horizontal line member. Oh, CB. Where's C? Am I from the end C? Okay, wait a minute. I may be doing this anyway. Okay, wait a minute. Okay, am I replaced? Okay, this is this. Okay, let's look at this. I'm trying to understand what in the world's. Okay, I see an A. I see a B. Where's the C? Okay, replace the load in the frame with a single result. Verify that its line of action intersects the vertical line along AC. Specify where it intersects on a horizontal line, member BC. That's got to be C there, measured from the end C. So I'm guessing that's C, but he didn't label it. Okay. Okay, so we'll take his member here, C. Okay. So we're going to do this in a much different way. The way I'm going to do this is I'm going to restate the question. The question is, an engineer wants to build this, but he wants to go to wherever and to buy his bolts. He wants to design this blue thing, supposedly metal, attached to this concrete down here, so that it doesn't come out. So what we're going to do is we're going to find out the actual load felt at A by all these loads. So what I'm going to do is I'm going to basically put in there the assumption. I'm going to assume that FAX exists. I'm sorry, that's Y. And then I'm going to assume here's force AX. And I'm just going to assume there's going to be some sort of moment here, which we're going to have the ground is going to have to supply so that this thing doesn't break apart. Now, the sum of the forces on all of this contraption is going to have to be equal to 0. Why? Because it's not accelerating anywhere. So it's static, which is why this course is called statics. But there also has to be a sum of the moments that equals 0. I'll give you a case in point. You're in space. You have a spaceship, which is a brick. You have a 100-pound thruster here and a 100-pound thruster here. It satisfied this. Sum of the forces in the y equals 0. It satisfies that. But yet if you did this, the first thing that would happen is this spaceship would start spinning. Why? Because you've just put a couple on it. You did not make it so this thing would stay static, would not start moving. Now, mass times acceleration y and mass times acceleration x. Yeah, if you look at the center of it, the center may not be moving anywhere, but it's rotating about the center. Why? Because it starts spinning. So you have to make sure that this is the case in order for something to truly be static. So what do you have to do? In this particular case, you have to put a twist on it that's equivalent to whatever that distance is and whatever this distance is, so that this moment would be d times 100, and then you got this other one, so you got to put 2. So in fact, you've got to make sure that all of these are behaved or satisfied. So I know the ground, I'm going to make the assumption the ground does this to it. Now once I get done, yes, I'm going to take this back and I'm going to do this to it, but for the time being, I'm going to start here. So you got 2 ways to do this. Since he did all your 3, 4, 5s for you, yeah, let's do it the easy way. First, I'm going to do my moment, so that sometimes they show these moments, and this is something you'll see a lot of, is you'll see these moments kind of stick to here. In other words, what I'm saying is, this is in the ground, and it's not, yes, this is equivalent to that, but often you'll see him drawing it in the ground where the moment is actually at. So that's why I'm going to change that. Plus, the other reason is so I can get it, draw these components here. So let's start with the x. Okay. So sum of the forces in the x equals 0. So I'll just go along there. Well, okay, there's no force in the x there. There's no force in the x there. Okay, there is a component this way, and it's 3/5 of 900. And it's going to the right. Now, look at his x and look at his y. So it is going to the right, and it's 900, but it's 3/5 of it because that's the component going to the right. Okay, now he's got one going back to the left. That is 4/5 of this 400. It's going back to the left. It's 400, but it's 4/5 of that. Okay. You would say I'm done, right? Except the ground is actually supplying or holding back by this amount. Now, you notice something, and I do this quite often. If I don't know where the direction is, I almost always put them in the positive x directions. And this being the case, you can see that this is a positive because it's in the positive case. So I'll always do them that way until we get to beams, and then there is some evidence or reason for doing them slightly different, which we'll talk about at that time. So that's it. So you have to realize I've got my loads here. I've got 1, 2, 3, 4, 5 applied loads. And that's it. So if AX B, okay, I have to move that to the other side. So, I don't know, what's going to happen here. But I have a funny feeling that maybe the f of x might be, there might be a sign change here. What's that snippet tool doing up? Oh, that's from the other class. Yeah, we might need that, but I doubt it. Okay. All right. Come on down. Come on down. $900 times 3/5 minus 220. So that's the force that the ground is having to put back on this object. Now, in a second, I'm going to redraw this a little bit. But for the moment, I'm just going to keep it as it's going. And then what I'm going to do, some forces in the y direction. Now, I'll make this positive, and I'll make, what happened here? I'll make that positive because that's weird. Okay, y component. Ooh, that's going straight down. Yeah, going straight up. And this component is going down, but it's 4/5 of 900. 900. And then you got this one going up, and it is 3/5 of 400. And then, lo and behold, I got my force, the ground's force, going in the positive direction. And so, I'm sorry, this kind of, I should have, well, I'm going to use the magic of the pen here. And just, whoops, accept. Okay, so what I get is FAY is equal to, now, I'm going to move all this to the other side, so I'm going to get 400 plus 4/5 of 900 minus the 600 minus the 3/5 of 400. Okay, so that's down there enough that I might be able to, okay, 400 plus 4/5 of 900 minus 600 minus 3/5 of 400. 280. Now, okay, here comes the fun. And in order to do the fun, I'm going to take this stuff and move it to the right a little bit. And I'll rearrange it a little bit, but that's good enough right now. So now, I'm basically summing the moments. Well, usually to find a moment about something, you basically sum the moment about that place. You can do it somewhere else, but I'm going to sum the moments. Now, is the object moving? Nope. Okay, so I'm going to also designate this being positive. That looks kind of funny. So let me do it again. That's positive. So I've got an MA. That's the one the ground is supplying back to this structure. Now, I'm going to go kind of in some sort of order. It really doesn't matter which order I go in. I'm going to go ahead and take my 400. Now it goes down and it goes this way, which is a positive. So it's plus 400 times its moment arm is 1.5, 1.5, and that took care of that one. This one on the other, now you have to remember, okay, I can do this. I can do transmissibility, move it right down here, And then I can say that is going this way. That is a minus. It's 600. And its moment arm is a half. Now, I got this one. This one can be broken into one that goes straight down in the ground, produces no moment about A, but this one does produce a moment. This force is 3/5 of 900 existing that far away from A. And it is going this way, which is a minus 3/5 of 900 at a moment arm of 2.5. Now this one, you could draw it two different ways, but the one I'll do is this one. This force is 4/5 of 400, but its moment arm, it's going like right here. This is the moment arm. It is going in a positive sense. 4/5 of 400, moment arm of 1, and that's all I got. So I'll use the magic of the pen again and copy each of these over. Not sure I really need to, but uh-oh, I forgot to hit the button. There's a button on the pen that I can hold down with my finger. And what happened here? Okay. That's what happened. Okay, so I'm going to have to move this, then move, ooh, uh-oh, and then move, oops, move this again. Okay, now I've got a problem because I'm bumping into each other. So I'll slide this even further to the right. Okay, so what does my moment look like? Well, my moment, I can move to the other side. The moment A is equal to. Okay, so I'm going to take the negatives and make them positive. And then I'm going to go back and take the positives and make them negatives, because they moved to the other side of the equation. And I'm going to slide down. I can't, but I can slide up and put this underneath it. 600.5 plus 3 divided by 5 times 900 times 2.5 minus 400 times 1.5 minus 400 times 4 divided by 5. 730. Okay, so here's what I got. Now, I'm going to go back, and this is a thought experiment. So I'm going to take a little extra time doing this thought experiment. So, in essence, here we go. What is a free body diagram? Well, a free body diagram is a diagram in which the body is cut free of its supports. So you're not supposed to see it. I was trying to get rid of it, but the ground is gone. And now, in replacement for that ground being gone, I've got a moment of 730. I've got a force minus 220. Okay, hang on. Minus meaning it's going in this direction. 220 and then a y force becomes 280. Okay. So, this is what an engineer would be interested in. They would be interested in, oh, I drew that, I didn't put the number. 280. This is 280. I better put these units so that I don't, that's Newton meter. You know, F times D is Newton meter. So that's what your moment is. So, here you go. There's your member in complete static equilibrium, just sitting there. Now, let's take a look at something else, and let's see if I can do this. I might be able to do it, might not sure, but I'm going to try this. And I'm going to use this funny scissor thing here, and I'm using the pen this time. So here we go. I'm going to do the best I can. And, ooh, and I sort of goofed there. I've goofed up several times here. This is going to look really, whoop, wait a minute. I don't know what I'm going to see. Okay. Well, that's okay. Oh, I forgot to clip that off. Shoot. That's good enough. I'm not going to go back and clip it again. I can clip it on the diagram I have here. I don't know if, in other words, I can clip it once. Here's what I can do. This works pretty good. Except here. Anyway, it's supposed to be meters. This time I'll do my best. Let's go back to the picture. This is a half a meter up. So this 0.5 meters. What's interesting, I'll go back in and I'll do a new clip, and this time I'll do this and I'll do, oop, give it to me. Give me my new clip. Boom. Now I can go back and drop this somewhere, and then I can delete this whole thing. Okay, so here's what I'm looking at. However, put them side by side. You'll see why in a minute. The magic of the pen. I'll just, okay, come on. What is going on? Copy. And I'll just put it down here and paste it, and then put it right there. Okay, so here we go. I want to find out, okay, I've removed all the other forces. It's either or. It's basically every reaction, every action causes a reaction. There's your reaction right here. As an engineer, you're interested in that reaction. What you find out is they're equivalent. So here's what I'm going to start doing. Okay. So transmissibility tells me I can move this thing up and down wherever I want. So let's move it up here. I didn't create anything, so I'm going to put it like at some point. Ooh, I didn't want to do that. I'm going to put it at some point up here, like D. Now, if I move this up here, if I move this, now I can move it here, I can move it back here, I can move it back here, But if I move it up to D, I have to look at something else and say to myself, hey, wait a minute. I have moved this up some distance D, so it's 220 times D changes the moment. What if I moved it up far enough so that it became that? 730. Okay, so give me a second here as I try to divide these numbers out. And also, I don't know why I don't just touch this to get it up there. 730 divided by 220. 3.3182. Okay, so I'm going to just say equals to 3. Oh, geez, I already forgot. 3182, I believe. Yeah. So here, I moved it up there. So I move those two forces. I'm going to ask myself an interesting question. I'm going to copy. And I'm going to paste. You got to be outside the realm of the selection. And then I do a paste. Now I'm going to do this. Copy, come back over here and paste. Ask yourself this question. Okay. Or is this equivalent to this, in which the moment is gone? Now, I have moved this 220 up some. By moving it up, I essentially created a moment. It turns out that that location right there is such that it's the same. In other words, and I'm not even sure. Actually, oh gosh, that was 3, and this is so. Okay, I have to. Let me do this. Okay, to scale, this right here is 2. So technically, okay. Technically, I had to move this point D way up here, say. And then I had to say, I'm just saying this because of scale. It has to, not everything has to be at scale, but the distance to D, this distance being 2, it makes sense that 3 is larger than 2, so the point D is way up there. Now, a couple ways you could put it. Let's say that's the case. It's 3.31 meters, whatever. Now, it depends on the way you want to do things, but here, let's do this. Take my 290, my 280. I'll put that number up here. I like my here, I may just try to see if I can select that instead of hovering over it. Can I select it? Maybe I can, maybe I can't. Oh yeah. So I'm putting it like that. Technically, maybe this vector needs to be a little longer because that's 220. Maybe make this about 280. Maybe that's about 280. Now, move this out to the side and you'll see why I'm doing that in a second. What happened there? I don't know. Oh, damn, what's going on? Okay. Your resultant vector is this. This is a point where I'm going to grab the ruler and get an approximation here. And maybe you'll see why. Come on. What are we looking at right now? Okay. So I can move this vector along this line at any particular point. Here's what I mean. I'm drawing it again in a different color that way so I can hopefully select it. Yeah. So this means I can move this vector anywhere along this line. I did not change the problem at all. So therefore, you can just drop it right there. And if you wanted to, you could, well, there, why not? Why not green? Green's a good color. You could figure out how far back this is. So in other words, if this is 2 to this point, then that's 1. This distance up to here is 1.3182. And if I were to look at this distance versus this distance, okay. Now, first of all, I'm running in to get against some problems here. First of all, we saw that. Let's get that out of the way. We don't even need that anymore. And this part right here is kind of cramping our style a little bit. So we're going to move it over. And it's the distance, although ugly drawn, it is the distance from here to the point of the application of the load back over there, in which you have the equivalent moment of 730, meaning that 3.3182 times that 220 should give you, let's double check this. There's your 3.31 times 220 should give you 730. Okay, so now that we've got that, if we want to know these distances, here's what's interesting. Let's look at it from a geometric viewpoint. This is distance 1. This is distance 2. Distance 1 to distance 2, if I ratioed these, distance 2 over distance 1 would be the same as this number over that number. Would be a ratio of 280 over 220. Oh, sorry, 220. Now, here's your deal. I know this distance is D2. So unfortunately, I wanted to do this the other way. Okay, D1 to D2 is as 220 to 280. I wanted to leave it because I wanted to find D1. So if I take D1, it should be equal to 1.3182 times 220 over 280. Gives you about something smaller than the other one. Okay, Okay, 220 divided by 280 times 1.3182, 1.0357. So that's distance 1. Now, I can't remember how he wanted this answer to be determined. Horizontal line, okay. Specify where its line of action intersects a horizontal line measured from the end of C. So I would say 1.5 plus 1.0357 becomes 2.5357. So now, hopefully that's the answer in the back of the book. 4.121. Oh, how about that? Well, it's not. So let's go at, okay, he says the resultant force is 3.56, I'm sorry, 356. Let's resolve each of these, and we may, if we have time, let's see, what time is it? We still got a little bit of time. So let's resolve each individual one of these. Okay. Let's see. He's saying the magnitude should be 220 squared plus 280 squared and the square root. Wrong thing here. Okay. Square root of 220 plus 280 squared. 356. So we're good. 356.08. He threw away the 8. So we check out there. Now, he's telling us 51.8 degrees. Okay. Well, first of all, which angle? Okay. Let's go back to here and find out how he asked that question. Horizontal line. Now, what we're going to get, and let me show you the way he probably thinks and the way we're thinking. Okay? Okay, so let me see if I can bring my ruler up. My ruler might still be set to that angle. How about that? It's weird. It's off a little bit. Okay. So that's where we were right there. So the question is, we got two angles. We got this angle and we got that angle. All right, so we can do the tangent inverse of either 220 over 280 or 280 over 220. Well, let's do both of those. Because the problem is, which one is he picking? I don't know. If you're going to tell us which one you're picking. Okay, tangent, arc tangent inverse 4 degrees of 220 over 280. There's your 38 and your 280 over 21. So there you go. 51.83. So, yep, okay, 51.83. We're good. So we got one of those. He didn't define which that angle was. Distance, 1.75. Now, this is the part that we did not get. And let's see if we can see why we did not get this. Okay. We moved ourselves up to the point where equivalently this load should be located that far apart. So in other words, the distance times that is 730. Now, that being the case, that was a half. Oh, I'm sorry. So if that's a half, and this is 1.5, and that's 1, then that is 1 plus 1.5 plus a half. That makes that 2. Wait, that makes that 3. Not 2. 1. This is 2.5, and then another one. So this means this distance is not 1.3. Mistake on my part. This distance is 0.3182. Error on me. I cannot add 1 plus 1.5 plus another half. The total distance from here to here was not 2, but was 3. That means this thing is slightly above here. Okay, my mistake. You probably caught it while I made it. This means that this ratio is this, which definitely changes that value to something besides the value I've got. Okay. And I don't have that listed, so I'm going to say 0.3182 times 220 divided by 280, 0.25 exactly. There's where my mistake was. If that's 0.25 exactly, and this is 1 and half, and then I move that 0.25, I get the exact answer, meaning that the total distance over to there was 1.75. So I hope that makes sense. But the key is, whether you look at it like you say, I'm going to take all these loads, or you say, I'm going to work off of all these loads, you get the same answer, barring the fact that you can add 1 and 1 and get 2, instead of 1 and 1 and get 3. So my stupid mistake, which usually happens, and that's kind of what happens in these things. So either or. Newton's law says every action comes up with an equal and opposite reaction. This means you can use this to answer this problem, or you can use this to answer this problem. But along the way, this is what the engineer is interested in finding out. What is the reaction at A? Because I got to build a piece right there to hold it. And so there you go. That's the end of the lecture.